Welcome to another class of basic organic chemistry. In today's class, we are going to look at the effects of acidity and basicity of organic compounds. First, definition of acid in terms of Bronsted-Lowry and Lewis. Bronsted-Lowry said that acid is proton donor, while a base accepts proton. A typical example of acid by Bronsted-Lowry are common HCl, sulfuric acid, while the organic section are any organic compound that can donate proton. Example is acetic acid or citric acid, because they have proton they can donate. While a base accepts proton, meaning they have lump of electron or unsaturated system, so there is space for them to accept proton. Acid accepts a pair of electrons, while base are the one that donates. Remember, Bronsted acid donates proton, while base accepts proton. By Lewis, acid accepts pair of electrons. A typical example of Lewis acid is hydrogen ion or trichloride, aluminum trichloride and zinc chloride. While typical base is hydroxyl group and ammonia. If you look at them, both Bronsted and Lowry are virtually saying the same thing in different ways. Because in terms of Bronsted, acid is one that donates proton, while base accepts proton. And the typical example of Bronsted acid is HCl, because there is always hydrogen ion to let go. And that of base is ammonia and hydroxyl group because of presence of lone pair. They are virtually saying the same thing from different view. The morphine is a compound that have both acid and base moiety in them. Morphine is a pain relieving tablet that, although that is very addictive. If you look at that, hydroxyl group, we have basic site and acidic site, because there is lump of electron making it a basic site, there is proton making it acidic site. Also, in terms of amine, you can see the lump of electron make it a basic site, so making this compound to act as acid and also as a base. The following molecule is a Bronsted-Lowry acid. Bronsted-Lowry said acid can donate protons, so hydrogen bromide is a typical example of Bronsted-Lowry acid. Which of the following is not a Bronsted-Lowry base? For a Bronsted-Lowry base, there must be lump of electron, there must be unsaturated system. So ethane is Bronsted-Lowry acid because it can donate proton. So that is the answer, is not a base but an acid. In terms of Bronsted-Lowry acid and base reaction, acid is going to give birth to a conjugate base, while a base is going to give birth to a conjugate acid. Remember, acid is going to donate a proton, while a base is going to accept a proton. So when acid donates a proton, what remains after donating is a conjugate base. So when a base accepts a proton, what remains after accepting that proton is conjugate acid. So that's what we call them acid-base reaction, which is a reversible reaction. Like I said in previous slide, a loss of proton from acid is going to form a conjugate base, while a gain of proton from a base is going to form a conjugate acid. So it's acid that is going to form a conjugate base, while a base is going to form a conjugate acid by accepting. In terms of Lewis, remember it involves acceptance of electron pair. So that is a typical example where electron pair is being accepted. Lewis acid accepting electron pair in terms of ammonia and hydrogen chloride. When electron pair is accepted, this lone pair of electron in ammonia become ammonium and chlorine become a base. Now, this base is going to give birth to a conjugate acid, and acid is going to give birth to a conjugate base, according to Lewis acid-base reaction. Label the acid-base and conjugate acid and conjugate base in the following reaction. Like said in previous slide, a base will accept a proton to become a conjugate acid, while an acid is going to lose a proton to become a conjugate base. So that is the same thing that you're expected to do here. Draw the products of the reaction. This is meant for you to understand what is conjugate base and how is it done in a reaction. If I'm looking at a reaction of methylamine and hydrogen chloride, in this reaction, the amine is my base, which is going to accept the proton, while HCl is an acid that will release the proton. So when it releases this proton, it's going to form a conjugate base. And when it accepts this proton being a base, it's going to form a conjugate acid. So that's how acid-base reaction is being written in terms of conjugate acid or conjugate base. In this case, we are talking about that in terms of Bronsted-Lowry acid-base reaction. Amine are organic bases because they contain nitrogen atom. And this nitrogen atom has lone pair of electron or unshared valence electron. So the more available this lone pair of electron are, the more we talk about whether these amine are strong or weak will be determined to see in subsequent slide. But remember that amine are bases because they have lone pair of electrons. Carboxylic acids are also a typical example of organic acid. In the presence of water, they ionize this water acting as a base. So when they ionize, about the strength of this acid. This strength of acid is determined by the ease by which this acid is able to donate or release proton. So if it happens that acid can easily release proton without stress, those acids are called strong acid. But those ones that can release it with stress are weak acids. And this is measured using equilibrium constant. Equilibrium constant is product over reactant. But because part of our reactant is water, and water is regarded as unity, always added when writing equilibrium constant. The essence of equilibrium constant in this sense is to help us to describe the strength of acid. Then it is being used, pKa is used than Ka values. In pKa is simply negative logarithm of Ka. So what does it say about strength of acid? The larger the Ka value, the stronger the acid. And Ka value being large, meaning that pKa value is going to be small. So large Ka value and pKa and small pKa value indicates stronger acid. So for acid to be strong, it's going to have high Ka value and low pKa value. Remember, from Ka to pKa is simple minus logarithm of 10. So it means that for me to get that, just cancel the 10 and anything that is exponential of that 10, make it to be positive and you're good to go. so you don't need to disturb your head on the calculation, especially those in biological science. You don't need to disturb yourself since I'm talking about minus logarithm of 10. So when I have 10, I cancel 10 cancels 10, and because there is minus in the logarithm, so negative cancels negative. So if I have 10 exponential minus 10, my pKa becomes 10, because minus logarithm of 10 cancels 10 and also make the minus to be positive. So that's how we got minus logarithm of exponential negative 10 becomes 10. Exponential 5, negative 5 becomes 5. So when I start tending towards positive, I'm going to have a negative value of pKa. But remember, the smaller the pKa, the stronger the acid. What are the factors that affect the strength of this acid? First is we're going to talk about structure of the compound, electronegativity of atom bonded to hydrogen, hybridization, inductive effect, and resonance. Now, in terms of structure of a compound, anything that stabilizes the conjugate base, remember how we got the conjugate base? Conjugate base is formed by an acid. When acid loses proton, it becomes a conjugate base. So anything that will make this conjugate base to be stable is going to make the acid to be strong. So when the acid is stronger than the conjugate base, it means that the acid is a weak acid. While when the conjugate base is more stable than the acid, it means that the acid is a very strong acid. The electronegativity of atom bonding to hydrogen. In simple terms, we are using methanol and methane as a typical example. Looking at their pKa value, methanol is 16, while methane is 43. And remember, we are told that the lower the pKa, the stronger the acid. Why is methanol having lower pKa than methane? The symbol is different of electronegative atom oxygen. That is what makes the pKa of methanol to be lower than that of methane. So the presence of electronegative atom bonded to hydrogen is going to influence the acidity of a compound. So the more electronegative an atom that is bonded to hydrogen, the higher the acidity. This also will be reflective in the pKa value being lower than usual. In terms of hybridization, we are talking about S character. X character determines the acid strength. The higher the S character, the more acid, because it's going to lead to high polarity and increase in acid strength. That is why sp3 has least S character, while sp have the highest S character. Because in sp we have ratio of S and P to be 1:1. In sp2 we have ratios to be 1:2. In sp3 we have ratios to be 1:3, meaning that S character is higher in triple bond, followed by double bond, and least in single bond. So in terms of acidity, triple bond is highly acidic, while single bond is least acidic. Remember, it's inversely proportional. So it means that least S character is going to be highly basic, while strong S character is going to be weak base, because base and acid are always inverse proportional. So when a compound is highly acidic, it's less basic. Just also note. In terms of inductive effect, we're going to use a compound called ethanoic acid and chloroethanoic acid. Difference between ethanoic and chloroethanoic is because of the presence of chlorine. Remember, chlorine is one of the compounds that we have to talk about of inductive effect in saturated system. So because of that, looking at the pKa, effect of chlorine being electronegative atom by inductive effect has reduced the pKa of ethanoic acid from 4.75 to 2.81. So the more we looking at this table, you can realize how inductive effect affects acidity. The farther away chlorine is from the carboxyl functional group, the lower the acidity. That is why when there is no chlorine, the acid strength is 4.8 from the second table, and when there is chlorine in carbon number 3, it got to 4. In carbon number 4, it got to 4.5. When the chlorine comes to carbon number 3, it got to 4. When the chlorine is on carbon number 2, it reduces to 2.9. So the closer this chlorine to carboxyl functional group, the higher the acid strength. And the more the number of chlorine, the more the acid strength. Resonance stability. In terms of resonance, we're talking about the more resonance stabilized a conjugate base is, the more the acidity. From the structure, we talk about anything that stabilizes the conjugate base made the acid to be very strong. So why is it that phenol is more acidic than alcohol, despite they have the same functional group, which is hydroxy? The difference is that in phenol, there is presence of resonance stabilization. So because the phenoxide ion in phenol can be stabilized by resonance, phenol is highly acidic, while the oxide ion of alcohol cannot be resonance stabilized. Hence, phenol is more acidic than alcohol. In terms of base, we are talking about in water, a weak base can dissociate, just like what happens in acid in water. Factors that affects the strength of a base: structure of the compound, hybridization and resonance. Structure of the compound: amine are basic compound due to lump of electron on nitrogen. So in a aqueous solution, amine is a weak base and is going to accept proton from water in a reversible acid-base reaction. In that case, if free amine is more stable than the conjugate base, than the conjugate acid, this amine is going to be less basic. Remember, in terms of acid, said when the acid is more stable than the conjugate base, that acid is weak. So when this free amine, which is a base, is more stable than the conjugate acid, that base is weak base. Then if the conjugate acid is more stable than the base, this free amine is a very strong base. And when there is presence of electron donating or releasing groups such as alkyl on this amine, is going to increase the basicity, because electron releasing or donating potential of alkyl will release more of electrons, making it highly electron rich, so thereby increasing the basic strength. The more the electron rich, the higher the basic strength amine. Typical example from the pKa value: realize that ammonia has just 4.75, and when there is methyl attached, it reduces to 3.34. When there are two methyl attached, it reduces to 3.27. Talking about the more the electron donating potential of alkyl, of methyl, the higher the basic strength and the lower the acidic strength. Whenever you're talking about base, remember the reverse is acid counterpart. Like it was discussed in acid, that the more the X character, the more the acidic strength. So the more the S character here, the lesser the acidic strength. The lesser the S character, the more the S character here, the lesser the basic strength. So the lower the S character, the more the basic strength. meaning that sp3 is more basic, followed by sp2. The least is sp, because highly acidic is the least basic, highly basic is the least acidic. That's the reason pyridine and piperidine, in terms of basic strength, piperidine is more acidic, is more basic and less acidic because of sp3, because of the S character is least. It is sp3 hybridized. sp2 hybridized is less basic, while sp3 hybridized is more basic because of S character. The lower the S character, the more the basic. The higher the S character, the more the acidic. So that's the same reason why piperidine is a stronger base than morpholine, because of S. This is also evident in their pKa value. The lower the pKa value, the more the basic strength of a compound. In terms of resonance, whether resonance stabilization or lack of resonance also affect the basic strength of amine. Example in amide, the presence of acyl group, which is electron withdrawing substituent, is going to reduce the electron cloud in nitrogen, making less electron to be available in nitrogen, hence reducing the basic strength. So meaning there is resonance stabilization makes amide a weaker base because of the presence of acyl substituent that makes number of electron on nitrogen less available for bonding. Question: calculate the pKa and which is a stronger acid. Looking at the Ka, remember higher, whenever you're talking about Ka value and pKa value, like I said in the previous slide, for you to know the Ka value and pKa value, minus logarithm of time. 10 exponential minus 10 and 10 exponential minus 41. Which one is higher? The higher one is 10 exponential minus 10. So higher Ka and lower pKa shows that phenol is a stronger acid than toluene, because when we talk about the pKa of toluene, we're going to have 41, while pKa of phenol we're going to have 10. So higher Ka and lower pKa confirm that phenol is a stronger acid than toluene. Which is the strongest base? Remember, in terms of base, we are also working with pKa. The lower the pKa is the same thing, the stronger the base. Meaning that water is a stronger base than ammonia and than methane. Draw the product and determine the direction of the equilibrium. In this, methane is an acid, while hydroxy group is a base. So at the end, methane is going to donate a proton to hydroxy group. So we're going to have methyl and water as a byproduct. Which of this base is strong enough to deprotonate acetic acid? Looking at their pKa values. Remember, the lower the pKa, the more acidic. So the one that can deprotonate this is 35 and 25, because they have higher pKa, meaning they are not very strong base. So they can do that. Chlorine cannot be. Chlorine is very strong base. Not using pKa, which is a stronger acid. The stronger acid is hydrogen bromide, because it can. Now the essence is that why is hydrogen bromide a stronger acid? Because it can, the bonding between hydrogen and bromine is very weak. So meaning that bromine can easily let hydrogen leave. Why is it weak? Because of the molecular weight of bromine is very high, making the bond between hydrogen and bromine to be very weak. So bromine can easily let hydrogen go because the bonding there is not strong. But if you're talking about bonding between hydrogen and fluorine, the bonding is too tight that fluorine cannot let go. And that's why in terms of acid strength, fluorine is difficult for fluorine to let go of hydrogen. So if I want to compare halogens, I will compare them by virtue of acid strength. It means that it's going to move down, increasing in acid strength, meaning that hydrogen bromide is more. After fluorine, we have chlorine, we have bromine, iodine. So in terms of hydrogen bromide, it is stronger than hydrogen chloride, and hydrogen iodide is stronger than them because they have higher capacity to let this hydrogen go because of the weakness of the bonding, which is as a result of the molecular weight. The higher the weight, the molecular weight, the weaker the bond and the easier for them to let the proton go, making the acid strength to be higher. So hydrogen bromide is a stronger acid than hydrogen sulfide. It is a stronger acid. The stronger acid, like we talked about, has to do with chlorine because fluorine, number one, the bonding between fluorine and hydrogen is very tight. Secondly, in terms of inductive effect, there is two methylene before the halogen fluorine, while in terms of chlorine we have just methylene. So the interaction between this halogen and carboxyl functional group is felt more by chlorine compound than by fluorine compound because chlorine is earth while fluorine is prop. So the answer is chloro. But in terms, assuming there's another case where we have the same compound like chlorine and I see difference in terms of carbon, more of carbon before carboxyl, it will still the one that have the smaller carbon between the halogen and the carboxyl. And if there's another option that have more halogens and the proximity to the carboxyl is higher, that one will also take a priority over this. So the more the halogen and proximity, that's what determines the strength of acid that has to do with halogens. Which is the stronger acid and why? The stronger acid is terms of hybridization, sp2 and sp3. sp2 is a stronger acid than sp3. Is not a Lewis base. A Lewis base must have unsaturation and number of electrons. So ethane is not a Lewis base, which is the second compound is not a Lewis base. Rather, is acts as an acid, not a Lewis base. Is a Bronsted acid. Can also act as a Lewis acid, which is not a Lewis acid. All are Lewis acid because they contain either unfilled valence shell or acidic proton. So they are all Lewis acid. I hope this is well understood. Remember, don't do chemistry alone. Ask your questions, drop in the comment section. As soon as you ask your question in the comment section, you'll be responded to. Till I see you in the next class, where we are going to be talking about benzene and aromatic compounds. Don't forget that chemistry is not difficult. Don't allow anybody to intimidate you. Just follow your pace. If it's possible for you to go through the slide twice or thrice, as much as possible, go through the slide. The more you go through them, the more you understand things you don't understand before. so that at the end when you enter exam hall for this course, it should be like the way you normally sing song without reading the lyrics. I wish you success in organic chemistry. Thank you.